Okay, here we go. So today we're going to talk about one of the very central topic of orcs, which is the clock system. I do not believe many engines have this kind of organization structure around the clocks. Usually, the main loop is hard-coded in most engines. It's not the case in orcs. Nothing would happen if there were no clocks. Clocks are like the base building of every time-related concept. And without a clock, there is no updates. Nothing will be called. It would just be like an inert repository of code that is never getting called. The way it works is that orcs will create two clocks for you. One is very minor. It's called FPS, and it's basically a clock that ticks every second, and it's to count the number of frames that have been rendered and just update the FPS counter. So it's extremely minimal. You can use it for your own purpose if you want to do something every second, but you can also create your own clock. So I would not recommend messing up with the FPS clock. The second one is a core clock, and that is really like the central nerve of orcs. The core clocks is the one that's going to tick all the internal of orcs, like triggering the rendering, like swapping the surface when the render is done, getting the input, getting the parameters from the window, updating the object, updating the effects, updating the physics. Everything it goes through that core clock, and we'll see how it works exactly and what we can do with it on top of this. But before going further, let's start with a very fresh project, and we're going to be very minimal today. We're not going to add fancy code or something like this. We're going to do everything on the fly. We just need to create a project. We're going to call it clock test, and we're going to use scroll because it's going to be easier to demonstrate later down the line how we do local time distortion on a per object basis. And we're going to add the mod so that we can have a background music, which is also a nice demonstration when we do time distortion. It makes it much more palpable when we do this. And our project is created. Let's load it with Visual Studio now. Let's see. Clock test. And there we go. So it's a brand new project. You can see that we have two source files. One is the base game. So again, nothing fancy here. The only thing it does, it binds the class object to the section object. It's going to initialize the module so that we can play ProTracker mods, and it's going to create an object called scene. And that's basically it. And you can see here there's an update function that is going to check for the quit input to just exit orcs. And this function here is actually been registered behind the scene by scroll itself onto the core clock, and it's going to be called every single tick through the core clock, and we're going to see exactly what that is. So something that's worth noting is that if we look at this prototype, we can see that there's a single parameter passed to the update function, and it's an orcs clock info. Let's see what we have in here. In the clock info, we have 4 different fields. The first one is a tick size. Basically, it's what defines the clock and how many times a second it should tick. So if the tick size is 60, it means that this clock is going to tick every single 1/60th of a second. Hello? Oh, hey, we have a newcomer. Welcome here. Oh, and before I continue, you can ask questions at any time, either through the text channel or just interrupt me. That's totally fine. And when I will give break to ask questions, you don't only have to ask questions about the clock system. You can ask questions about anything, really. I'd be happy to answer any orcs-related questions. Today we are focusing on clocks, but I'm happy to branch out if needed. So going back to our clock info structure, we have the tick size that defines how many times a second the clock should tick. We have the DT. DT stands for delta time, which is the time that has been elapsed since the last time the clock has ticked. And this should match, usually most of the time, the tick size itself. But because now the computers are not, like they run a lot of background processes, and there's a lot of things going on affecting what your own process can do. The DT can be different from the tick size. This is the actual time that you will receive that has been elapsed since the last tick. And the time is just an accumulator. It's just accumulating DT every time there's a new DT, so it tells you for how long the clock has been running in seconds. And then we have a list of modifiers, and we can see that if we go up, we have like 4 different kinds of modifiers, but we will come back to this a bit later, and I will explain exactly what they do and what you can do with them. The last thing that we're not going to dive deep into, but we should need to know, is that every clock, when you register function onto them, you will also provide a priority. And this is a list of priorities, they are hard-coded. They go from lowest, lower, low, normal, high, higher, highest. And it's just defined in which order the functions are going to be called inside the same clock. So the priorities are for a single clock. And inside that clock, it just defines the order of the function calls. You have to know that in the core clock, there is one priority that is not used by orcs at all, and which is meant for use by the developer. It's a normal clock. And that if you actually, the one registered by the scroll here is actually on the normal priority. And if you run code here, I mean that this code will run after everything that's highest, higher, and high, but before everything that's low, lower, and lowest. So basically, usually we have in the higher one, we have fetching the input from the OS and these kind of things. And on the lower one, we will have like updating the internal of the object, updating the physics, and this kind of thing as well. So just know that because of these priorities, we get some kind of ordering inside a single clock. So let's just see what happens if we run this. Actually, you know what? We're just going to do a real quick update on the config here. We're going to remove the full screen because that's not very friendly when streaming. We're going to remove the vsync because if we want to play with clock, we don't want to be limited by the actual vertical refresh. We're going to go for 1080p screen height 1080, and we want to force showing the FPS counter so that we can illustrate a few things. And let's run this. Okay, so that's our base project. Oh yeah, no, you don't see it because I need to do another things. I have a virtual monitor, so I'm just going to say I want it on the second monitor. This way I don't have to drag and drop the window every single time. There we go. So you can see here right now, we run at 60 FPS and it seems pretty stable. We hear the music, we see the object having like a flashing, color cycling effect and rotating. And so that's not too annoying right now. I'm just going to remove the sound and music and only keep the object. And that will also, that will come back later when we're going to want to illustrate time distortion, but right now we don't need it. So let's illustrate the DT. Very simple, we're just going to go here. In our depth function, we're just going to log it. So log, and we're going to display the delta time of our core clock. And it's stored inside the clock info that we get. And there we go. And now, when we run, I will bring this window in view. You can see that we get to print our DT every single time. But already there's something weird here, is that the DT is super precise and it never flickers or anything. It's exactly the same value all the time. And it's precisely 1/60th of a second. But how? Right now we removed vsync, so we are not constrained by the vertical sync. So you would expect like orcs to run as fast as possible. And you would also expect like variation in the delta time. Well, there are two things happening behind the scene that are just default configuration, but that can be changed. And to learn about those, we're just going to look at the settings template. Inside the settings template, you can see that the core clock can be defined with the clock section. And actually it also works if you use its name. Its name is just core, it's the same thing. And it's just using a template for a clock. And a clock has two properties. One is the frequency, and one is the modifier list. The frequency is what is going to define the tick size, but we can see that we can give it like a numerical value, or we can give it the value display. And if we use the value display, it's actually going to sync with the display refresh rate. And it turns out my display refresh rate is 60 Hertz right now. So if I were to set the frequency to display, it will match my 60 Hertz. And it turns out that the default value for this is display. So behind the scene, what we have right now, even though we didn't specify anything here, it's the same thing as having like our clock frequency display. Actually, you know what? We can just use its name this way. It will be less confusing after. The core clock is display, and that's why we get the 60 FPS. But there was a second thing. The DT was extremely precise and was not faltering or anything. And it's because of the modifier list. There are 4 different values for this: fixed, multiply, max, and average. I'm going to brush over the average one because it's not very interesting, but I will come back later to it. But right now, the interesting one is the fixed one. The fixed one is just saying that the DT you're going to receive is a fixed value. No matter how much actual time has elapsed since the last tick, AUX will tell you that this amount of time precisely has elapsed. And as it turned out, it defaults to fixed -1, and -1 means that it exactly matches the frequency of the clock. So if your clock is running at a frequency of 30, the DT will be 1/30th. If your clock is running at a frequency of 60, the DT will be 1/60th, and so on and so forth. So again, by not using any value, it's the same thing as having a modifier fixed -1. So this is the hidden default values, but we can change them. Let's say that we do not want any modifier. Now if I run this, we'll see that our DT, which is here, is not as steady as before. And there's like tiny variations. Those tiny variations seem like it should not matter because really we are like below milliseconds or like really in the realm of microseconds. But those variations will like do some kind of snowballing, and they will introduce what is perceivable microstutter. And that's why by default AUX is using a fixed DT, and that is going to try to match the one coming from the clock. And that's the reason behind it. But if we were not fixing the DT, you can see that it's have like tiny variations, and it's actually giving to the code the exact precise amount of time that has elapsed since last tick. So, okay, so we already have this one, and here we have the display one. If we set the value to 0, what's going to happen is that AUX clock, the core clock, is going to run as fast as it possibly can. There is no fixed delta time, no fixed tick size, and it's just going to run very quickly, apparently like up to 2,000 times a second or something like this. And you can see that the DT is all over the place here as well. And what is important is that no matter what the DT is, you can see our object is still rotating at the same pace, and the color cycling also happens at the same pace, even though our frame rate is super inconsistent and channel over the time. And it's because of that DT value, and we're going to come back to this. And it's even like more obvious if we build like a release build, because in release we actually run at 3,000 frames a second or something like this. And you can see the DT at the bottom right of the screen. It is all over the place and very inconsistent. So right now, let's go back to like our frequency of display, and let's check the other kind of modifier we can use. So we've seen the fixed one. So basically, if I comment this, we're going back to 60 FPS with a very, very fixed DT. You can see it is 1/60th of a second at the bottom right. Let's try the different modifier we have here. So another one was the maxed one. The maxed one defines how big a DT could be if your program stops executing for a fixed, like a large amount of time. Let's say that your system freezes for X or Y reason, or like on Windows, it's super easy. You just have to hold the window title and drag the window, and it will freeze all the updates inside it. And when you release it, you probably don't want to have like a huge gap in time, otherwise your object will teleport, it will wreak havoc with physics, and it's not what you want probably. And here we can actually, we need to remove one property in the render, which is called mean frequency, which prevents the render to go less than a given frequency, and by default it's 10 Hertz. The render by default cannot go less than 10 Hertz frequency. We're just going to remove this limitation here so that I can illustrate my thing here. So if we have no modifier list right now, and we're in release, let's go back in debug so that we can actually see the log on the side. So bring the log here. If I hold this, you can see that the update pauses. And if I hold it for seconds, when I release it, you can see that there was a DT of 5.9 seconds, meaning that this frame here took 5.9 seconds. And you could see that the arc's rotation did a huge jump. Like if I let go right now, up, it like did almost like a quarter turn instead of just a tiny increment. Because here we waited for 11 seconds this DT. And that's exactly what the max DT is for. If I say, no, I want to max at 0.2, no matter how long I will skip it. Okay, so I have to bring this window every time in view, it's a bit annoying. And if I'm going to stop here, and I keep it even for seconds, or no matter how long I want, if I let go, you will see that the DT cannot go bigger than 0.2. And that means also that our object is not going to jump more than 0.2 seconds at a time. And so there is no like huge jump like of a quarter or full turn or something like this. It's just going to be like a tiny minor hitch. And that's what the max value is about. The last one is for very, very specific use, it's average, and basically it's going to take all the value of the DTs over the X number of last frame and make an average of it. So basically it's going to be like a low pass filter. It's going to prevent spike. Even if you want to have like different like variation of your data time, it's going to smooth those variations to make sure there's no like huge spikes, like very high frequency changes. That's the average one. But it's most likely you're not going to have to need it. And the one I kept for the last one is the multiply. And the multiply is very important for us because it's how we do time distortion. And we're going to try it right now. So if we go back to here, we're going to keep the fixed one. So mean that when we run, it runs at 160s. You can see it at the bottom right. But let's give it also like a multiply. Oh, and yeah, it's a modifier list. Actually, modifier can stack upon each other. So you can have both the fix on top of the max, on top of the average, on top of multiply. They can all mesh together. So let's say that we want a multiply value, and we're going to say multiply 2. What's going to happen now is that our core clock, it's going still to tick at 60 Hertz, 160 Hertz per second every time it ticks. But the DT it's going to give to our code is going to be twice as big. So our code will think the time is actually flowing twice as fast. And it will result in our object rotating twice as fast and our color cycling also going twice as fast. And if we look at the values, which I lost, well, there they are. You can see that now it's not 0.016, it's exactly the double amount of time. I mean that the entire system right now is going twice as fast. And you can actually see that opening the console is going twice as fast. And the, the multiplier, the modifier list can be changed at runtime. So if I say clock set modifier for the core clock, and I say I want the multiply to be 5 times, you can see that our object is now rotating 5 times faster, and that our console is also reacting 5 times faster. And same thing, if I set it to 0.2, it's going to be 5 times slower. You can see that our console is moving 5 times slower. The color cycling and the rotation are 5 times slower. And you can see our DT is also 5 times less than the original value. Our update still happens 60 times a second, but the delta time that is given to our code is 5 times lower, and that results in time distortion. Like we are running 5 times slower than the actual world around us. And that you can see it affects the entire system, because the entire system uses the core clock to run. Actually, a very quick thing I can show you. If we look to the aux.h here, there's an execute function. And the execute function, that's the iOS one. Let's take the desktop one. There we go. And the execute function, what it does, it has a main loop, like you would expect. It's a tiny main loop. All it does in this main loop, basically, it's called aux clock update. And by calling this, all the clocks that exist inside aux, so the two I mentioned earlier and the one that you can add on your own, thing like this, are going to be updated. And that's the only single update point inside aux. Everything is driven by the clock system. And that's why first it's very flexible, and we can do things like time distortion, like we can distort the time for the entire system, but it's also like very easy to modify. Like we can definitely take pieces out and add pieces in, just because everything is built upon that clock system. So we've seen that we can distort the entire time for the entire system, but it's unlikely that you want to do that because it also affects your inputs and everything. So what you want to do usually is like doing time distortion either for all your simulation, your object, or even just for like a portion of your object. Like think of like, I don't know, slowing down the enemies, for example, if you have like a specific power up like this. Or even if you want to slow down your entire like a simulation of the game itself, maybe you don't want to slow down your menus and you want your menus still be as reactive even if your game is going 10 times slower. So we need to learn how to do localized time distortion. And that's where our own clocks are going to come into play. So if we go back here, we're just going to stop messing around with the core clock entirely, and we are going to see what we can do. Right now, we have a scene that only has one object, and this object has a bunch of properties, a graphic, angular velocity, and fx list, and there's a property called clock. And if we say that we want a clock to be my clock, all we have to do is define a section called my clock. And if we start it now, and our object is running correctly, if we were to open the console, you know what, actually, we've seen the log for the DT. I'm just going to remove that log because it's going to be annoying otherwise. There we go. So without the spam of this, if I open the console, and this object, I can actually check all the structures that are currently existing inside aux. And you can see that on our object, we have applied not only the graphic and fx pointer, but now we have a clock, which is called my clock. But because we haven't defined anything, and you can see it here with the color, it's better. But because we have not defined anything for my clock, it's just running normally. And you can see that our object is completely like unphased, it's just running as usual. But we can modify the clock, like we did with the core clock earlier. So clock set modifier my clock. I want to change the modifier, and I want it to be like 5 times faster. And you can see that our object now is rotating and color cycling 5 times faster. It's because my clock is only linked to that specific object. And same thing if we want to go like 5 times slower, it's going to affect this object. But you can see that this time the console is not affected. And even if I were to create another object that inherits from it, so let's say I want to create config set, and we're going to call it new object. It's inheriting from object. Oh, actually, let's do it in config. It's going to be much faster. We're going to create a new object here. New object. And our new object is going to inherit from object. And it's actually our new object that's going to use the clock. We're going to move our object to the left. So let's say something like this. And our new object to the right. So now, right now our objects are exactly in sync. But if we were looking at the structure, we see that we have a clock on our new object, And if we were to modify that clock, you see that the new object, which is on the right, is actually affected, but the one on the left is not affected. So we have done local time distortion. And you can see it works on the fly. And if I can actually add and remove clocks on the fly as well, like if I find my object on the left and I say now object set clock, my clock, you can see that now they are both under the influence of the same clock, and I can simply just remove it, and now it's back to normal. So you can do any local time distortion, and you can add it or remove it on the fly without like much hassle. I mean, it's a single command here, and you can do it in code as well. What if we wanted to affect like a lot of objects? Of course, we could apply this like ourselves on all the objects we want and change the clock and things like this. The thing is that we can have as many clocks as we want, so like we can have like different version of time distortion, but we can also apply a clock on a full hierarchy. And to illustrate this, let's put everything back here, including our sound and music. So if I run it like this, and let's actually give a time distortion right from the beginning, ModifierList, multiply, and it's going to go twice as slow. You can see now that by default our new object is affected, but the original object is not affected, the music is not affected either, it's only local. And what if I wanted to affect everything? Well, as we've seen, our scene is the parent object for both object, new object, sound, and music. So if we were to set a clock on that scene, instead of setting it here, it's going to affect just itself. So far, not very interesting. You can see that our objects are not affected, the scene is affected, but So how could we do this? Well, it turns out that we can apply a clock recursively using a command. So what we can do is, here, cursor, we can find our scene, and we can set its clock recursively. So on our scene, we want to set my clock recursively. And now it's affecting all the children at the same time. You can see both our objects are slowing down, we can hear our music slowing down, and we can change now, we can manage the time distortion by simply changing the value of that clock, like even slower. And that's where the sound is very, much easier to perceive than just rotation and things like this. And same thing, if we want to go faster, we can hear the effect it has on object. You're going to tell me, okay, all those properties are handled by Arc itself. What if I want them to affect my own code? Well, exactly the same way as before, and we're going to see how it works. So let's go back to 1. I believe that's all I wanted to see here. And now if I create a new object, new version of the object, actually, you know what, let's put it back to slow. There we go. And if I wanted to create a new object, it's going to be unaffected by this clock because it's not linked to it. And you can see that the new object is just running its life at a regular speed and not 5 times slower. Okay, now let's say, fair enough. We want to see what happens to my object here. So we're just going to keep an object, we don't keep the rest. And we can just keep we can keep my clock here. And the object here, we're going to, let's see, put it to the left. Yeah, like this. And if we run it, we have our rotating object to the left, if everything goes well. And that's this. We can have even put it a bit more to the left. Let's see. So now that we have this, let's see what we can do in our code. See, we have an update function, and here too we have a clock info that's passed. This time it's not a pointer, it's a reference, but it's the same idea. So we could log it, as we did before. So object dt, and we can just display it. And we can see that as before, you can see that it gets this dt here. And we can see that if we were to put a clock on this object, which is object here, clock, my clock, and my clock is running, let's say, 5 times as slow. If we create it, not only our object is going 5 times as slow, but the delta time we get is also 5 times slower. It's been affected. That means that if we wanted to move that object, let's say we want to make it move to the right, and we're going to go like very trivial approach. We're going to get a vector. We're going to get its position. We're going to update its x value. We're going to say, okay, move 1 pixel to the right, and we're going to set its position back. Let's see what happens. And we can see that our object is moving 1 pixel every update to the right. Okay, fair enough. Remember that our core clock right now is using a fixed display frequency. What if our frequency was different? What if our frequency was actually run as fast as possible? Whoop! What happened there? Well, what happened is that we're using a fixed value inside our update function. Every time our update function is called, we're moving 1 pixel to the right. Before, we were being called 60 times a second. Now we're being called 2,000 or 3,000 times a second, and our object is flying. And exactly the same way the other way around. If we were, sorry, if we were running at 30 FPS, our object would be moving twice as slow horizontally, and that's not what we want. So what we want is to be completely independent, and to do this, we need to use the DT as before. Let's say that our speed, we actually want to go 100 pixels a second to the right. All we have to do is multiply this value by the delta time. In that every single time this function is going to call, we know how much portion of a second has elapsed since last time, and we're going to multiply our value with this, and mean that if we've been called 60 times a second, this is going to be 1/60th, and then we're going to take 1/60th of 100 pixels, and we're going to move accordingly to the right. So if we do this, and I'm just going to remove the clock for a second, I'm just going to remove this. If we do this, oops. If we do this, oops, what happened there? 100 pixel DT. Oh, I didn't rebuild. No. What did I miss here? VFX. What am I missing? Let's see. Is it? Okay, let's go back in time a bit. Let's remove the clock. Let's go back with our frequency. Okay, that is normal. We get the value, we multiply it by the dt, and we set its position, and that should be like time independent. So let's work. What if we... Yeah, okay, so I'm not sure what was going on. I think I was building when the binary was still running, and that's probably what happened. Well, in any case, this is what is supposed to happen. Right now we are running at 4,000 frames a second in debug, or 3,000, 4,000, and you can see that we're still moving 100 pixels to the right, and it's completely independent of the frequency of update, because we're using the DT. And same thing, if we were moving now at 30 Hz frame, even though we're only updating 30 times a second, the object is still moving 100 pixels to the right per second, and it's a fixed value. And this value is also affected by the modifier set on the clock. So if we have the clock here on our object, we should go 5 times slower than 100 times. Oops, yeah, that's maybe a bit too much. Let's put 0.5. Okay, so we're going twice as slow as 100 pixels a second, and no matter what our how many times we're called by seconds, like even if we have like 4,000 updates a second, and that's the issue there. Why is this happening? Okay, so it was not the explanation I had before, and I'm not understanding what's going on here. What did I miss? Do I have multiple my clock? No. Oh, I do have multiple my clock. Oh, I have a clock here. Wait. Let's clean everything first. Okay, so we have one object. We're going to stop playing with this. We're just going to keep my clock. And here, I don't see. Okay, we're moving at 100 per second. And here, if I were actually changing the DT, core modifier, yeah, okay. So the DT is sent to our clock, and now we are going to run 5 times slower. We could run like 10 times slower, or we could run like 100 times slower, and it's barely moving. Or we could go back to like twice as fast, and then everything that is sent to our code here is going to take into account the clock that is attached to the object, and the DT is going to be taken into consideration as well. So that's for the basic time distortion and modifier, how we can apply this on like a localized object or not. Let's see another concept that comes with clock, and those are called timers. Timers are if you want to delay the execution of your code later at a given date, but you want to trigger this logic right now. So to illustrate this, let's say that our object is not moving anymore. So if I build it like this, it's just going to rotate here. And let's say that we want now to be able to like shoot bullets, because it's the easiest thing to do. So we're going to have our spawner, and it's going to be a gun, and our gun is going to spawn bullets. It's going to spawn 1 bullet at a time. It's going to do it immediately, and it's only going to spawn a single bullet, so only 1 bullet in that timer before it deactivates. But when it deactivates, I want it to reset. So it has a property called auto reset, and means that it will have spawned 1 total object. It's going to deactivate, but it's going to be primed again to be reactivated. That's what we do with auto reset. And of course, we need to define the bullet. So let's say that the bullet, we want the graphic to be the same as the object. We want it probably to be like 10 times smaller. And I like the color cycling effect. So color cycle. And we're going to say you go 200 pixels horizontally to the right, and let's see what happens. Oh, see, upon start, we shot 1 single bullet, and then the spanner deactivated. Let's put some logic here. Let's say that we only want to do it when input has been triggered. So if the input has been activated, fire, we're going to enable that spawner. So arc spawner, enable, and we're going to retrieve the spawner inside the object, which is arcs object get structure, and we want the internal arcs object of our scroll object, and we want to retrieve the spawner in it. And we're going to activate it every time the fire has been triggered. But we also need to define our fire input, because right now we don't have one. So here we're just going to say key space is down to fire. And every time I'm here, every time I press space, I can shoot. And you can see that my little object is going there as being, and you know what, I like my bullets to be straight. So I'm going to come back to my spawner, and I say use rotation equals false, meaning that it's not going to use the rotation of the parent, and my bullets are going to keep straight. Okay, fair enough. Now I have a gun, I can shoot every time I press the space, I can shoot as fast as I want, but what if I wanted to have like auto shoot, like repeating? If I keep space pressed, nothing happens. So how about we ask to reset our input after a certain amount of time? And we can use a timer for this. Arcs input add global timer, why input, sorry, arcs clock, sorry. Global timer. Global timer means it's going to use the core clock to register this. We want a function called reset input. We want to do it like after 0.1 seconds or like 0.2 seconds. And we want to do it once, and we want to reset the fire input. So you can see that we need to define this. So let's go check our global timer, and you can see that it takes the aux clock function. We can copy the prototype. And now that we have it, we want a void fast call. It's called reset inputs, and it's taking those parameters. And you can see that the parameters is basically the clock on which it runs, like the information of the clock on which it runs, and the context, which is like what we gave it. And we gave it like a string, which is a fire. So we're going to start with this. We're going to retrieve that string, which is our input. So const string and context. And now we are going to reset its value. So aux input set value of that input, and we're setting it to 0. In that, after 0.2 seconds, my input is resetting to 0. I mean that if my spacebar is still pressed, it's going to trigger again after 0.2 seconds. But it's going to do it once. So what we want to do is only to do it if it's still active, like if my spacebar is still active. So if my input, aux input is active, and the one that we've been sent, we're going to reset it, and we're going to register ourselves again. So we are going to basically do this. And this time we can just reuse the input we've been given, and mean that every 0.2 seconds is going to reset, and if I keep space pressed, you can see is 0.2 seconds is going to shoot again. And right now everything's fine. Let's see if it works well when we add like a local clock. So on our object, we have still my clock, and let's say my clock, the modifier list is going to be a multiply 0.2, so 5 times slower. Let's see what happens. It's not affected. Our object is running 5 times slower, but our gun is still shooting as fast as before. It's because we're using the core clock here. We are not using the clock that is set on the object, but we can retrieve that clock. So aux clock. And same thing as before, aux object, we want to find the structure, and inside our internal aux object from the scroll object, we want to find the clock. If there's a clock, we're going to register the timer on top of it. If there's no clock, we're just going to add a global timer. And the only difference is that here it's called timer, and you give it a clock. So if we have a clock, we're going to register to it, and if we don't have a clock, we're just going to use the core timer. So it will work with any kind of object.
Ron, you're having connection issues here.
Oh, sorry. What did you miss? I will try to do my best. Can you hear me? Hello, hello?
I think it's better. What does...
Okay. I'm sorry about that. I'm not sure what.
Is it good for you, Sausage, too?
Yeah, no issues at all.
Oh, okay.
Okay, awesome. Okay. Good to go.
Okay. Don't hesitate to ask me questions if it broke and you lost part of the explanation. I'd be happy to come back over it. Right now, I'll just continue, just in case. And so it will work with any kind of object. If there's a clock, we're going to use that clock. If there's no clock, we're using the core clock. So let's see what happens. And you can see, the repeats, the first time we did have like the 5 times delay, like because the 5 times slower. But after that, we went back to the regular 0.2. But if you remember here, we're adding a global timer as well. So we are not honoring the regular clock coming from here. So the way we need to do this here, instead of doing add global timer, we're just going to use the clock that has been used to call the reset input. And it turns out that from the clock info, you can actually retrieve the clock. It's called aux clock get from info. And you pass it the clock info. And now, every single reset will also be affected. So I have still the space pressed, the fire is still pressed, and you can see that it goes 5 times slower. And now if we were to change the modifier of my clock and say that actually I want it to be twice as fast as the original, well, it's going to work as well. And let's say I want it to be 10 times as fast. same thing, or twice as slow. And you can see our code can be affected by the time distortion, even with timers. As long as you're using the clock information passed to you in any update function, and any update function inside Orcs will have this information. As long as you're using this information, you will be consistent with the time of the system, no matter if you're running like at 60 FPS, 100 FPS, 1000 FPS, and it will also be consistent with time distortion. So it's very important to always use the information of the clock. The entire system is built on top of this. It's very flexible, but you need to remember to use it. If you don't use it, well, you're going to break your stuff. If you use it, you get things like time distortion, local time distortion, global time distortion. Everything is consistent, and it will work just fine. And I believe that's all I had really prepared to showcase today. So if you have any questions, be they related to clock system or like anything really, I will be happy to answer them.
Yeah, so a question surrounding, most monitors are running at 60 hertz, but I guess it's prudent to test your games on something like a 75 hertz system or 120, just to see the effect of, I'm sure we've written many games and just put them out like that, not being aware that running it on a faster display rate is going to give a totally different play speed for someone, right?
As long as you're using the clock info, it won't matter. Like, for example, let's say we're not running at 60 FPS, our clock, but we're running at 100 FPS. Because we're not using VSync right now, I can run at twice as fast what I'm displaying. So let's say that the frequency of my core clock is 120 FPS. That should not affect the result because we're using the clock information. And you can see it's exactly the same result as when I was running at 60 FPS. Even though at the top you can see it's 120 FPS. So no matter the speed of the system on which you run, no matter the fluctuation of the time and thing like this, everything will be consistent as long as you're using the information from the clock. This example with the gun is very concrete because in this very specific example, I can do it without all code at all. I can do it entirely in config, and I can show you how like in a second. But if you need to do something more like contrib or like more, not contrib, but more advanced than just having like a frequency on the spawner, this is important to know that the timers can be tied to the clock of an object. But let's say now that I just wanted to like have my spawner rate vary based on the clock attached to my object. All I have to do is say, I'm going to come back to this actually. Let's say this line is the important one, the enable spawner. I'm just only going to enable my spawner if the input is active. Arcs input is active, fire, which means that this is never going to use. I can even delete it. And I just have to change the way it's been defined here. Remember here, when my spawner was defined, I said I want a total of one object, I want to auto reset. Let's get rid of this. And we can just put the delay here. So if I want my spawner to have a nominal delay of 0.2 seconds between two bullets, that's all I had to do. And now if I keep press space, it's still affected by the time distortion. So if I put it back to 1, it's going to shoot 0.2 seconds. If I say I want it 10 times faster, it's going to shoot 10 times faster. And if I say I want it to be 5 times slower, it's going to be 5 times slower. So in the case of like a spawner rate, the code I was showcasing for the timer is not necessary. It's much easier to do it this way, like just enabling it based if the input is active or not, and letting the internal of the spawner handle the frequency. But it was to showcase if you have like any other kind of logic and you want it to be affected by the local clock of your object, you can still do it with timers and things like this. And of course, any properties that are on an object are affected by the clock. So we've seen it for the pitch of the music, like the how fast the music is playing. We saw it like for the FXs. We saw it with the physics, with the movement. It's the same thing with like if you have like animation on an object, or if you have like timelines on an object, commands and things like this. Everything is consistent with the time, and everything is going to use the DT. All the code internally in Orcs will use it, and your code should use it as well if you want to be completely time independent, like frequency independent and things like as we've seen here. Right now we are running at 100 FPS, and if we run at 400 FPS, it's going to be the exact same result because everything again is using that clock DT. So let's go here, and you can see that my shooting is the same as 400 FPS that it is at 60 or 120. So yeah, it's very important to always use the DT in your update function. Everything that is time dependent should always use the clock info. You have it on your object in scroll. You have it in any function you register with regular arcs as well. Every time you call arcs clock register, it's going to pass this parameter to you. A scroll is just doing it behind the scene. We can actually probably find it. So like arcs clock register. And if we look at scroll, you can see that there is a static update here, and that's the one that's calling our game update. And you can see that that's what it's doing. It's registering on the core clock. It's registering the static update function, no context. It's going to use a module ID. So I didn't touch that, but module ID is that because you can actually plug and unplug modules at runtime in arcs, and you don't want an update function that has been registered for a specific module to run if the module has been unplugged. But that's outside of the scope of today. And you can see that by default is registering as a normal priority, and it's also registering a second update, which is a camera update, which is at the lower priority, in that every time your main function update is going to be called before the camera update. This allows you to know the current position of all your objects before you move your camera and not have stutters. Like you can see even in commercial games when they release, sometimes you will have stutter, especially if you go on moving platforms. You can see your character moving and stuttering, and same thing with camera. It's because of these priority inversions. You always want to update things on which you rely first, and so your camera is probably going to be updated after all your objects have been moved. And that's why there are two different update functions with scroll. One is called update, and the other one is called, actually, if I go back to scroll here, and the other one is called, that's in the scroll base, camera update, if I'm not mistaken. Yeah, update and camera update. But if you don't override it by default, you don't get a camera update. But in any case, behind the scene, it's always using the clock module of arcs, and it's just functions that are attached to this and are going to be receiving the clock info structure, letting you make sure that your code is completely frequency independent of your system and will be time consistent if you want to do distortion or if your frame rate varies for X or Y reason. And any other questions? Sorry if I started rambling there. Let me actually check the chat because, okay, that's it. Typical use case for time distortion is clock. Well, there are definitely use case for like if you want to slow down enemies, for example, which is like usual prop thing like this. You can also do it like if you want to slow down time, you know, like upon a hit in a lot of fighting games, you have like a tiny slowdown time upon contact, or if you want to do it like on a kill camera, you know, when the time just starts distorting and slow down and then resumes. All these can be done with local time distortion or global time distortion. I would recommend local. This way, you can still have your menu that is independent of it, or like your inputs or HUDs or anything. So time distortion can be very useful. It's not a system that is going to define your gameplay, though maybe it will actually. I made a game jam back in 2009 called Mushroom Stew, and one of the guns was local time distortion around the character. So it created bubbles where everything slowed down around you. So all the projectiles, all the enemies will slow down when they enter that zone, and that was part of the gameplay. But yeah, that's the feature is there, and it's good to know that everything relies on that system of clock, which I believe is not common to many engines, if any. So it's good to know that it exists. And yes, the matrix style effect on the player. It's often, you know, like a small amount of time distortion, like to accentuate like a hit or anticipation before like an attack. Think of games like Batman, you know, like before you do a knockout, the time will slow down, and then it will accelerate again, and that's super easy to do with clocks. I see. Okay, do you know how stable the liquid fund physics? That's a very good question. Extra care have been made so that it should be very stable by default. And the way it is that by default, you don't want like different DT on the physics update. It's going to break your simulation because it really relies on a very constant delta time. And the way it works, if we're going back to let's see. Just need to hide this window. Okay. If we go back to the settings template here, there's a physics section, and you will see there's a couple of properties with this. One is called the step frequency, and this is used for fixed step world physics simulation. By default, it's 0, meaning that it's going to have a variable DT, but because the DT by default in ARCS is fixed to your refresh rate, it's basically as having the same thing as a fixed step world simulation. But let's say that your DT is all over the place. Like you want to be able to support like varying DT on your game for X or Y reason. I'm not sure why, but you could force the physics to still update with a fixed rate. And what that means is that it's going to truncate. Let's say you say, okay, now we moved for a 30th of a second, but I want my physics simulation to only run at a 1/60th of a second. Well, it's going to run 2 steps of 1/60th inside by just using the frequency. And you see that actually that's the default behavior inside ARCS. It's going to use a 1/60th update for time slicing the update of the physics. So it's done internally inside the plugin. Then there's also, like if you want to interpolate the updates, like for example, let's say your simulation runs not, for some reason your physics is very costly and you only want to run it at, I don't know, 10 times a second, but it's going to be very choppy movement, right? Well, the interpolation will make sure that it's going to interpolate at the rendering rate based on the values that are coming from the physics, so that you will still have a smooth movement even though your physics is only running 1 frame out of 6. So these two here are definitely what are going to be interesting. And the last one is the iteration per step, is how many time you want to iterate to refine the physics simulation per step. The more you do it, the more time intensive it gets for the simulation, but the more precise your result gets. So it's like a knob you can turn on Liquid Fun, which is based on Box2D. It's an internal knob. Unless you really want to have a very specific feeling or like very tight control over the physics simulation and you know what you're doing, I would recommend not using the iteration step. But the step frequency and interpolate, the interpolate especially, which is set by true by default. So that even if I run at the physics simulation at 10 times a second, the interpolation by default will be there, and I will have like a smooth movement. But you can ask not to have it if you don't want interpolation and you want the raw value coming from the physics. But yeah, so just to summarize, we are time slicing the simulation of the physics to make sure that it remains stable and does not explode, as you would expect if you have like a too high DT or like too much variation in delta time from one frame to the other. So it's done for you inside the engine. Does it answer your question? Perfect. Any other questions on this topic or any other? Originally, I thought that I would go much faster through the clocks, and I was like thinking of showing other things for resources, but I don't think we will have time. Can you please comment how non-clock-centric engine are affected by the design choice? Any example? Well, yes, you can see example with old games, for example. If you run old games on newer machines, some games are going to run very, very fast. It's because they were meant to run at a very precise, fixed time step. And the new machines are running faster and they update faster, and then you get something that are unplayable. It's less the case now with engine for the last 20 years, but the engines from last 20 years do not give you the flexibility of doing like this kind of time distortion. I mean that you will have to add your own control of the DT and how you're going to modify it and how you're going to apply it on different parts of the simulation. You're going to have like invasive changes in some engines. It was the case with Unreal, for example, back in Unreal 2. I don't know if it's still the case with Unreal 4 or 5, but we had to do like a lot of invasive changes to do this kind of things, whereas it's built in with Orcs. And everything is just registering thing on the clock, mean that your main loop is not hard-coded, and that's why, like for example, like kind of things like the mod plugin or any plugin that requires registering to the core clock, they can add on the fly. They can extend the engine by just how do you say? I cannot say my word. By just grafting themselves onto that clock simulation, and you can easily extend it, or you can actually remove it. Like if you want to pause for X or Y reason, you want to remove like I don't know, like the rendering, you can just deregister the function that does the rendering from the core clock. It's not going to be called anymore, and you won't have any render anymore. But the rest of the simulation will still run, no matter like completely unaffected. The parts are completely independent, and what ties them together is that clock system. Hopefully that answers your question. I see we have one last question, maybe? Also, don't hesitate to ask them live if you enjoy the typing is not mandatory. Yep. Someone popped in and popped out. We usually recommend leaving the core clock in the default state and using custom clocks when specific behavior required. Yes, I would, unless you know you need a one-to-one relation with something that exists already, like let's say physics or something like this. But otherwise, if you want like specific logic, like let's say your AI runs at 10 Hz, for example, create a new clock and run your AI on that clock. Because if you start messing with the core clock, you affect the entire system. And maybe that's something you want, but it's likely that you don't want it. And something when creating clock on like on the fly, like I did with my clock was just a bracket, like a section config. The clock is created and it's going to be ticked even if nothing is registered to it. But the clock exists, so I can reuse it in my code. I can add a timer as you seen earlier, but I can also register functions to it, and it will be affected by the modifier that we put on it. So yeah, so the answer is I would recommend using your own clock to do like more exotic things, like having an AI that runs very low frame rate or something, low frequency or something like this. I should probably read those questions because the people watching the streams or recording later do not see that, or I need to find a way to stream them as well. So basically the question was, would you usually recommend leaving the core clock in its default state and using custom clocks when specified behavior is required? The answer is yes, I would recommend that. Question before was, can you please comment on how non-clock centric engines are affected by the design choice? Well, back in the days, it meant that you could not run on different machines without affecting the entire simulation if you were not careful. And even with more recent engines, mean that everything is hard-coded and not flexible. So adding like new feature, extending it, mean that you have to modify the actual hard-coded loop. And you cannot pause like part of it easily as you can with Orcs. Do you know stable liquid fan physics plugin is in presence of time distortion? It is stable. You have control of how you want to time slice it or interpolate the result, but by default, everything will be time sliced, and mean that the DT that will be used for updating the physics simulation will be constant, no matter what your DT in the world is, and you can define that constant. By default, it's 1/60th of a second, but you can have your physics run at much lower frame rate if you want, or a higher one, depending on the result you want and the precision you want. There's always a trade-off between the processing power and the precision of what you're getting. Any update on Sausage Orcs ID? Well, that's not to me to answer. There was also, I've been reminded recently that there was a very nice effort on animation ID, both by Enuberam and by, I'm sorry, his name is slipping from me. A contributor from Brazil that moved out. Oh, God, I'm so sorry. I cannot remember his name right now. In any case, those could be interesting to look into because they could be good bases. They were quite advanced as well. I would still love to do an editor at some point, more than what I have in the scroll editor. But because I really dislike traditional GUI concept, I want to work on this first, and it's probably going to take me a few years down the line, especially as I'm doing it as a hobby and not as a full-time development. How is timer granularity affected by the associated clock? Specifically, if a timer is given a shorter duration than the parent's clock time step, or a non-even multiple of the clock time step. There is an accumulation of the DT. So if you're not running, if I understand correctly the question, otherwise let me know if I misunderstood. But if the clock is running, let's say at, you have a frequency of 60 Hertz, and it's actually running at 60 Hertz because that's what your system is doing. We are going to keep the accumulation of the whatever leftover is on the clock. We're going to tick multiple times if need be. Like if you reach multiple DT, we're going to call and update the engine multiple times to catch up. And whatever partial amount of frame is left is going to be put in an accumulator to be added to the next frame to make sure that we have consistency there. It's not a perfect system, but it's by far the most stable I've seen, and probably also one of the most advanced because a lot of engines don't bother with kind of things, and they can easily run at a nice smooth rate at the nominal or multiple frequency. But when you get into like 50% more or 30% less, it becomes like G3 and things like this. We've tried really hard with R to remove this as much as possible. It's not perfect by any means, but we've put a lot of effort. And you can actually look at, let's actually see if I can show it here. If I'm opening the source, the source for the clock system, and if we are going to go to the update function, you can see that everything is there. So like we're getting the actual system time, which is very precise and coming down to the nanosecond. We are going to go through all the clocks, and for every clock that is not paused, we're going to, well, that is, if it's a display clock, we're going to get the display tick size from the refresh rate coming from the rendering module. But otherwise, we have a partial DT that we're going to accumulate. And once the partial DT has reached the next tick size, we're going to trigger all the register function on it, so the callbacks here, and all the timer as well. So those are the timer callbacks that are going to be called. They're going to be called X times. There's like a repetition that going to remove them when the repetition has expired. And then we're going to call all the clock based on their priority. They actually been stored into a linked list based on their priority, and they're going to be called. And then we're going to reinitialize the partial DT, and we're going to look at how much delay we have. If we need to actually delay the clock again, we are going to ask for a pause on the system to relieve pressure and not make sure we're using 100% of a core. So if we need to wait for, and there's actually like a bit of adjustment here. So it's 1 millisecond. If we need to wait for more than 1 millisecond before the next update, we're going to relinquish control of the thread to the OS and ask us to be awakened 1 millisecond before we should, to make sure that we are not too late. On some system, we might end up too late, and that's why you can actually play with us with this value here. But otherwise, we should be awake again ahead of time enough that we will not miss the next tick size. So as you can see, we're doing like partial time accumulation. We're going to go over all the tick size. We're going to tick when we need it, and we're going also to relieve pressure and relinquish control of the thread to the OS to make sure we don't do 100% of occupancy of the core. And that's it. And yeah, I think that should cover this question. Any other questions? Well, I will take that as no then. Thank you everyone for being here and for all the questions. And again, if you have more questions, don't hesitate to ask them on Discord. And we'll see you next time when we talk. I'm going to be on vacation for like a month and a half, so we won't have another live session at least until late August, early September. So I will still be there to answer any questions, but I won't be able to do any live session until I'm back from vacation. Well, thank you everyone. And I wish you all a good day, evening, depending on where you live. Have a good one.